1, 2, 3, sync.
It's DC.
Morning, folks.
Good morning.
Good morning.
Thank you all for being here. How was your break?
Great.
Good.
Great, good. Little rainy. It was a little rainy.
It was raining.
Rainy indeed. Okay. Well, hopefully you're rested. You all got your homeworks in before the break. I'm going to do on Thursday, so that way you have Friday off. What? See, look how non-monstrous I am. See? All right. Okay. A little bit of housekeeping business. So, some of you have asked this great question. Oh, what's today? 5th. My God, what is today? What's the date? 18th. 18th. It doesn't tell me. I'm on my iPod right here. Thank you. Thank you. In the common era. There we go. All right. So a little housekeeping business. Number one are your project proposals. I've almost done grading them. I can give you all feedback so that way you can move on to phase 2, okay? So once I say go, basically, I'm going to give you 2 weeks for the sort of the dynamics draft is what we call it, okay? Again, the thing you shouldn't underestimate is simulating your system, okay? Make sure it works right, okay? All right? So I'll get that hopefully today. I'll finish up the project proposals, get your feedback on that, okay? In terms of homework, okay? Expect 2 more assignments, okay? Okay? Next one's gonna be on trajectory optimization. Okay. Might be a few more quizzes as needed, as I feel like people might need to just brush up on some of the concepts. Again, I always try to make it so the material is at your disposal, right? Okay. So make sure you cover it. Okay? So any questions for me on the housekeeping business here? Okay. All right. So let's do a little recap because we just had spring break. We just got back from it. Maybe need a little refresher. Is what we were talking about. Okay. So let's refresh on 2 things. Okay, on 2 topics. 2 topics. Okay. One is on trajectory optimization. And the other was linear optimization and LTI systems. Okay. What does LTI stand for, friends?
Linear.
Linear time invariant. I heard from that side of the room. What about that side of the room? What is it?
Linear time invariant.
Oh, also correct. Also correct. All right. Fresh on those 2 topics, okay? Now, the art of trajectory optimization often came down to how we formulate the problem, how we set up the problem. And we talked about a couple methods. Does anyone remember the couple of methods that we used, what the sort of buzzwords were for trajectory optimization that we talked about?
Single shooting.
Single shooting was one method. Any other ones?
Direct collocation.
Yeah, direct collocation is another one. And I'll leave a conspicuous space in the middle for what I thought I heard. Direct collocation is another one. And what about this one?
Multiple shooting.
Multiple shooting. Okay. Okay. Does anyone like give me in their own words what the difference was between, let's say, these shooting methods and the collocation method? Any idea? In their own words. Yes, Angela.
Don't you need your control inputs and states in the collocation method? We don't for the shooting methods?
Yes, you're right, absolutely. So the direct collocation scheme, for one, in your decision vector, we'll call W, right? So for shooting, your decision vector is going to have all of your U's, U1 through UN, at a minimum. It needs that. Okay, those are your inputs. That's a difference. And whereas for co-location, you have your inputs, U, and your states, X, as part of your decision vector. That's one difference between co-location and shooting. What about the relationship with the dynamics and how you integrate them? Is there any difference between shooting and co-location methods? No difference at all. Good luck. Yes, Logan.
I think co-location, like, it checks if the physics actually work out, but for shooting, it kind of just, it gets to the where you want without caring about.
That's a very close way of putting it, okay? So the way I will put it is that, like, so single shooting, or these shooting methods, use time marching integration methods, like ODE 4.5, Euler's method, take your pick. You start at your initial condition, you integrate it forward, that's a simulation, right? And you see where it goes, right? You shoot, right? Whereas the co-location scheme, which you were describing, kind of just checks at key points in the middle and checks if the slopes of those derivatives obey physics. Because the slopes of the states, sorry. So basically, keeping in mind that your dynamics look something like this, right? Those are your dynamics. State space. Dynamics. So if you're looking at x dot, that's state over time, that's your slope. Therefore, if your trajectory has a slope at a particular point, it better be equal to this, right? That's what co-location does. Co-location checks the physics at key points along the trajectory. Wacky, wild, kind of non-intuitive. But we showed how quickly in our coding lectures how it can optimize those problems. Pretty crazy, right? It's gonna get faster. Okay? Co-location. Co-location methods check the physics along the trajectory at co-location points. Okay? Just a little reminder of that. So that's the left half of the screen. You have these trajectory optimizations methods, okay? And co-location, it can be fast. One thing that's nice about it is you don't have to do this time marching integration. Every time you want to evaluate your cost and constraints, right? Instead, you just have these little equations that we wrote up. My gosh, was it 3 weeks ago now? Right? We put them in MATLAB and everything, and we said, hey, there's our co-location constraints. We check physics. It doesn't require time marching integration, so it tends to be faster. Also, the derivatives of them tend to be more accurate because you don't have to use finite differencing. Finite differencing is the method where you check one variable and then you push it a little bit and see did the slope go up or down. Which means you got to do more simulations. Anyway, the other half was this linearization. So recall we have our state space form, x dot is equal to f of x of t and u of t, okay? And that f, that can be nonlinear, right? Can be nonlinear. Pardon the brief aside. This is for dynamics that are continuous, one where you have time derivatives, continuous time. Hence, it's a function of t, and t is a real number, right? Okay? This is a little aside, so I'm going to put it in red. Okay? You could also have discrete time, if you wanted. You could have that the next time step, x sub lowercase k plus 1, is equal to some function of whatever your current state is, xk, and whatever your current input is UK.
Should there be X on?
No.
Okay.
This is a little aside. So this is when, this is discrete time. Great question, Angela. Okay. So imagine you're only looking at the state of your system at particular intervals of time. Okay? You're only looking at it once every second or something like that. You're almost looking at a slideshow. You're almost looking at a slide. What's a slideshow? The right thing? Right? You look at those different snapshots, right? If you're only looking at those snapshots, right, you could then formulate the dynamics and saying, well, you know, I'm not really looking at some continuous time derivative. I'm just saying, hey, my next state is some function of my previous state and also the input I'm doing at this time, the thing I'm doing. This is the international symbol for input. Know that for your controls conferences. You do that, people are like, ah, that person knows what they're talking about. The input dance. No. All right. So, this, some people might come across this in the literature. It's like, hey, where's the of t? That's for discrete time, okay? Sometimes we will do this in we will use this analysis in legged locomotion, where we say, hey, we're only going to look at snapshots in time where a foot hits the ground. So, what happens in the middle, we don't care. And this actually makes the analysis really easy, but that's in discrete time. Anyway, F can be nonlinear though. This is where you have your Cars Lightning McQueen scenario, where you could turn right to go left, for instance. Right? Or if you turn hard enough right, you go left. As opposed to if you turn a little bit to the right, you go right. Nonlinear, wild, okay? You could turn it into x dot is equal to ax of t plus bu of t. This is LTI state space form. Okay. I'll just label a few more things here. This was the input. And that's your states. Okay. So you have your x dot is equal to ax plus bu. I know I've had you all recite that. Right? And we showed that, hey, that if you find some x star where f of x star equals 0, otherwise called a fixed point, you can get that. You can find what we'll call x tilde dot plus a x tilde of t plus b u tilde of t, where x tilde is equal to, and this is supposed to be of t right there, I apologize. Make that a little nicer. Apologies, friends. You can do that on an iPad, you cannot, it's unfair. There we go, beautiful. Where x tilde of t is equal to x of t minus x star, and u tilde of t is equal to u of t minus u star. Okay? That's a fixed point. Fixed point x star and u star. So there's also some control input associated with that fixed point. It can be 0, that's fine, so long as the f of x f of that is equal to 0. And I forgot the u of t, the u of u star here. Apologies. It should be u star. I see a question over there. A question? No? Was that your question? Am I hallucinating? Yes and yes. Okay. All right. Okay, so what was nice about, anyone remember why linearization or turning something into LTI was a good idea? Anybody? Did we do anything with LTI? No? Yeah. Maybe at the very end of the last lecture, which I'm sure you all remember vividly, from the coding lecture, okay? Once I had that A and B matrix, I can just come up with controllers. No problem. Real easy. Okay? It let me come up with controllers of the form U is equal to minus capital KX. So I'm going to put this in red so you can have linear controllers. U of t is equal to minus k. I've literally boxed myself in here. Let's see. There we go. That's it. U of t is equal to minus kx of t. Very simple controller. This is what you implemented in homework 1. I just gave you the k. How do you find the k? Well, there were methods such as pole placement and LQR, which requires some more derivation than we're going to go into today. Okay? But the point is that linear systems have a ton of tools at their disposal. You can look at that A matrix and tell you, is that system stable? If I poke it, will it come back to my equilibrium point? Yes or no? Can I even come up with a controller? We talked about controllability. Does anyone have that in their notes? Controllability? Right. No one has that in their notes. Okay, all right. So, all right. Some of you nodded, some of you didn't. So I'm going to assume the worst. Okay. Good. All right. I could be hallucinating the entire last 3 weeks. Part of this is for me as I get up there. Okay? Yeah, and the controllability allowed, basically you were able to check just by looking at this A and B matrix whether or not this system could possibly be controlled. If B was filled with zeros, there's nothing you can do with U to do anything, right? That's the trivial example. But there are all kinds of non-trivial examples, like if you had different motors, let's say you had 2 motors on your 2 degree of freedom arm. Here's my arm. Okay, 2 degree of freedom. That, right? What if I put 2 motors on here? 2 motors, 2 degrees of freedom, but they're both here. This thing's gonna flop around. Nothing, right? But is it controllable? Who knows? We can check using the controllability matrix. You can check your notes for that. Okay. All kinds of stuff you can do with linearization. Okay. Well, what could you do if you had an LTI system and some nice fast trajectory optimization methods? An interesting question. I'm glad I asked it. Okay. So, trajectory optimization thus far we have used to calculate open loop control, otherwise known as feed forward. U of t, where our U is just dependent upon time. Does that use sensor feedback? No, I don't see an X anywhere in there. Don't have our state, right? This is, you can think of it as planning in a way. If you did we did our trajectory optimization of our jetpack student, jetpacking to class. That came up with some control input for the force coming out of the jetpack over time, right? More or less, it was a plan to get from A to B by putting the right amount of thrust in, right? Okay. Now, what would probably happen if we gave that student a bump and applied that same U of t? Any ideas? I see shaking heads, which I'm assuming means death.
Overshoot, probably.
Overshoot, probably. Could undershoot, probably. What if you bump them down? bump them down, right? It's open loop controller. It doesn't have that feedback from the state, right? Okay. Now, so if you recall, there's kind of a good reason why people tend to use these trajectory optimizations as feed-forward plans. Because you can just run them once, and you come up with a plan, and then you execute the plan, and you hope it works. Okay? That's because it took maybe a minute or so, maybe 10 seconds or so, to solve that optimization problem. Okay? So it's not that practical sometimes to say, okay, I'm jetpacking around. Logan gives me a bump innocently. I assume it wasn't intentional. Okay? What if I could pause time in that moment and say, oh, I'm now here. And I'm going to pause time and I'm going to run a new trajectory optimization where this is my new initial condition and I plan a way to get here. That'd be a pretty cool thing. Just replan on the fly, right? In fact, what if every single time I got bumped, Eric's got that look in his eyes. Can I bump? Yes. Yes, you can, Eric. Okay. Bump me again. Boop. Okay, I'm pausing time. I'm going to replan. Replan over and over again. Wouldn't that be nice? That would be nice, but again, it takes too long. Can't wait 20 seconds while I am zipping off on my jetpack somewhere wrong, right? Not that practical. But what if we could make it faster? What if instead of taking 10 seconds, it took a millisecond? Hey, not only could I see, hey, was I bumped? If yes, run a new optimization. I could just run a new optimization every millisecond, just in case I got bumped. Hey, where am I now? Where am I now? Replan. Where am I now? Replan. Where am I now? Replan. Over and over and over and over again. Okay? If you have a linear system, an LTI system, you can make trajectory optimization converge very, very quickly by turning it into a convex quadratic program. And for a lot of these things, they'll solve under a millisecond with modern tools. You did this with your QP with your homework with QPs, right? You had very simple QPs, okay? But you now have the tools for setting up these QPs. Now all we need to do is come up with a trajectory optimization that is a quadratic program, QP. Okay? So, if trajectory optimization can be made fast enough, then it can be used for closed loop or feedback control, where you would have some block diagram where you have some place you want to get to, maybe some reference, we'll call it ROT, we want to get somewhere, okay, and then we have a block here, which is our plant, and here's our feed closed loop controller. In fact, instead of R, we're going to make this, I apologize, it's going to be X desired, okay? This is going to be X of T. This comes in positive, this is subtracted off negative. So here's our feedback, right? And here's going to be our controller, which actually can be a trajectory optimization, TO. Okay. this approach of trajectory optimization loop has a cool name. Like, I think it's an okay name. Called Model-Predictive Control. What I meant to say is that it's the coolest thing with the most bleh name that I've encountered in robotics. Model-Predictive Control. So it's the process of generating closed loop control inputs via trajectory optimizations on LTI system dynamics with evolving initial conditions and a receding time horizon. Okay. Model predictive control. I'm going to put it this, otherwise known as MPC. MPC. All right. It's a bit of a dry definition, but here's what it's doing in practice. What model predictive control does. Okay. All right. And for this, I'm going to need a volunteer to come up in front of the camera. Anybody? Hunter, you're up. Come on. Round of applause for Hunter. First class of spring break. What's your name, sir? Hunter. I knew that. Thank you. All right. So I am going to be an LTI system.
Okay.
Okay? You believe me?
I do.
Thank you, Hunter. All right, so I'm going to be an LTI system. All right, and I actually have a task for a controller, which is I want to get to right behind you. Okay, right behind you. All right. So I am going to have a plan. So I'm going to be controlled with model predictive control. All right. But you are taller than me. And so what you're going to do is you're going to gently push me at times I tell you to. All right? Okay? All right? In fact, if you could stand just a little bit to the left right there. Okay, so I have a clear path here, right? Okay. Now, all right. So I'm going to start my model predictive controller. I'm going to run a trajectory optimization. I did it. Okay? I'm going to go that way. All right? You came up with the trajectory. You believe me, right? You all have done this in the coding lectures, right? Trajectory optimizations. We just did it. Plan. All right? So what I'm going to do is I'm going to execute the first little bit of that plan, which is like go forward, right? Okay, so like one step forward. Okay. All right. I now measure where I am. Here. Boop. I want to plan to get to there. I did it. Believe me?
Yeah.
Good. All right. Fantastic. So I'm going to do a new plan. I'm going to execute that new plan, the first step of it. Boop. But now, I have an adversary in Hunter. All right? Okay. So I'm going this way, and Hunter's going to give me a gentle shove. Ready? Oh my goodness. I survived. Thank you. All right. Okay. This is my state. This is my new initial condition. I run a new trajectory optimization, which is now to get there. Right? It's a little different. Okay? But it's okay. I just ran my trajectory optimization. I have a new plan. Okay? So now I'm going to take this first step on this new plan. There. But Hunter does not give up easy. Gives me another push. Ready? Wah. Good. All right. I have a new state. What do I do next? Run the new plan.
Yeah.
New plan. Right? And Hunter, amazed by my resilience, gives up and goes back to his seat. So thank you very much. Right? And I continue until I get here. And guess what? Even when I'm here, I still keep planning. How do I get from here to here? Do nothing. All right. Cool. Do nothing. Cool. Do nothing. Cool. Cool. And if Hunter ever re-emerged, gave me another push, guess what? Coming back. Right? That's what model predictive control is. So it's always thinking, always planning. So it actually makes it really flexible in doing stuff. Okay? If I'm over here, if suddenly I transport it over here, I have a new plan. It's going to get me over there. Right? That makes sense? Okay. A few details that are a little different than my example. One is that we don't plan all the way to the end of some goal. We just plan for a certain period of time ahead. Okay? All right? So some number of seconds in the future. So maybe I'm planning 2 seconds into the future. All right? And wherever I am and whenever I am, I'm always planning 2 seconds into the future. So you can think of it as the horizon of time. It's 2 seconds into the future. And every time I move forward in time, as we are wont to do in this space-time continuum, I'm a little forward in time. Where's my time horizon now? Still 2 seconds ahead of that, right? So wherever we are in time, the horizon moves forward or recedes. Okay? So that's why I call it a receding time horizon. Okay? So what you will typically see is when you go look online for model predictive control, is that you would have time, and then you would have 2 plots here. You'd have one for time, one for state over time, one for control input over time. And it will say, hey, I have some kind of goal that I want to get to, or some kind of system, some kind of state I want to track. It'll be like that. And you start here, and then you come up with a plan, a trajectory optimization that looks like that, and it requires some kind of control inputs that might look like that. And then what you do is you step forward in time, some small time step, we'll call it capital T sub s, called a sampling time. So you would execute on this plan for this period of time, and then you would re-optimize and come up with a new plan, which maybe looks like that. Maybe looks like that. I know I was throwing lots of colors out there. And then you execute on that plan for another TS. Okay? Right. Which means you would be applying this control input over that time, and then you see where you go from there. Like, okay, now I actually go, there, I don't know. Okay. So the idea is you keep planning, and you keep executing a little bit of that plan, and then you measure.
Professor, the
Yeah.
sampling time's the interval, right? Like
Yep.
not the actual value of time?
Correct, it's the interval, that's great. So let's call, so the sampling time is the interval between measurements and between measurements. Okay? And what are you measuring? You're measuring your state. Let's put this as a series of steps for you, okay, make it a little bit more clear. So, MPC. Number 1, measure state. Number 2, perform trajectory optimization. With fixed time horizon T. Number 3, execute optimized control input U of t for TS seconds. Number 4, go to 1. You measure your state. For mathematical completeness, we'll call it x of t. 2, you perform a trajectory optimization with fixed time horizon t. 3, you execute an optimal control input, U of t, optimized control input for TS seconds. Okay. Does that comport with the step that the things that I did with Hunter? Does that make sense? Followed that process? Okay. Pretty neat, right? Again, it's dependent upon us being able to solve this trajectory optimization fast enough. Yes, Logan?
What's the time horizon again? Is that the dashed line you drew?
It would be the total length, the total time period which for the plan. So let's put this on. So see this plan right here. This is our first plan here. The time horizon t would be that time. The difference between the starting time and the ending time. Okay. How far in the future are you looking?
How many samples you've done?
What's this is good. This is pointing out a thing I should clarify. Thank you, Logan. Okay. When we did our trajectory optimizations, do people recall that like sometimes we'd have a variable for capital T? That's sort of the final time of our trajectory optimization. Sometimes that could be a variable in our decision vector, right? It's a decision that you want to make, right? At which point, is that variable fixed? No, it's literally a variable, okay? But you could also always say that, hey, t equals 3, right? So it's not a variable. That means it's 3 seconds from now. And that's what capital T is. And there's a good reason why we are fixing that to be a constant, all right? It's because if it's not a constant, when we set up our trajectory optimization, it becomes a nonlinear program. Nonlinear program, eh. Quadratic program, eh. If we fix it, that time, the constraints are all linear for an LTI system. I'll show you how, okay? Because that's the thing we have not gotten to yet, is how do we get this trajectory optimization to go so fast? I mentioned it in pieces. It's the fact that our system has to be LTI, okay? And we need a fixed time horizon. And we're going to use direct collocation. Okay. All right. So, if your problem has 1, LTI dynamics. Sorry. If your trajectory optimization problem, specifically, your trajectory optimization problem has LTI dynamics, and 2, a fixed time horizon, capital T is a constant, okay? Then direct collocation will create a set of physics constraints that are linear. That's huge. In order for something to be a quadratic program, what must the constraints be?
Linear.
Linear. What about for a linear program? What must the constraints be?
Linear.
Linear. Do we like linear programs? No, that's a subjective answer. Doc, I like linear programs.
Yes.
What's attractive? Okay, you all know how to suck up to me, I get it. No, that's great. It's great. So, well, what's so great about linear programs? Anything good about them?
They're simple.
They're simple. How are they simple?
The local minimum is also the global minimum.
Yeah, local minimum is also global minimum. Is there another word for that? Which rhymes with schmonvex?
Convex.
It's convex. It's convex, right? And quadratic programs, do we like them? Yes. If their Hessian is positive semi-definite, they are also schmonvex. Convex, right? Local minimum is the same as the global minimum. We can do a local search, and there are so many ways to do local searches with them, okay? Which means you solve them fast. Key aspect of them is that the constraint must be linear, right? Now, what's the other thing that must be true for something to be a quadratic program? Constraints are linear. What about the cost? Hint, it's in the name. Quadratic. Glad we remember. Okay? All right. So, that means, actually, let me prove this fact to you that they must be linear. Okay? So let's say we have some dynamics, x dot of t, some LTI dynamics. X dot of t is equal to a x of t plus b u of t. Okay. A and B are matrices, of course. This is the system matrix. This is the input matrix. Okay. Those are your LTI dynamics. X dot is equal to ax plus bu that Angela loves so much. Okay. Sorry to speak for you. All right. Okay. Then you have your physics or your defect constraint for direct collocation. So let's do our physics constraint. And let's just say with forward Euler integration. Okay? Which means that the next state, we'll call it xk plus 1, is equal to the previous state xk plus x dot at time k times delta t. We've seen that Euler's method before, forward Euler. Look familiar? Okay. Well, we know what, at a given time, the state derivative is equal to this, right? So that means that x at some time k, x dot at some time k, is equal to a times the state at that time k, plus, yeah, you think you know, Angela? What's b times uk? Sorry to interrupt. No, sorry, I'm hearing voices. This isn't good. Stop talking. All right. All right. You agree with me there? Right? So now I can take this, substitute that into there, right? So that means that xk plus 1 is equal to xk. And to be clear, this is our physics constraint. Right? Do you agree with that? Okay, our physics constraint is equal to axk plus b. Oh, I'm losing my dang mind. I apologize. Give me a second here. Use your eraser technology. Sorry. Is equal to xk, that's this stuff up here, plus x dot, and x dot is equal to a xk plus b uk times delta t. Therefore, xk plus 1 is going to be equal to, I'm going to distribute this delta t here is going to be equal to xk plus a xk delta t plus b uk delta t. And I'm going to factor out, and this is a scalar, so I can put that on the other side, so I can put that in the middle there. I'm going to factor out xk to the right here. Xk plus 1 is equal to the quantity of something times xk plus b times delta t uk. Again, all I did was I put the delta t in here. That's a scalar, so I can move where that is in the matrix multiplication. That's okay. If delta t was a matrix, put me down. Okay? Let me do that. All right. And here, it's going to be equal to the identity matrix plus a times delta t. Could you factor this out? In order to make all this math work, there has to be an identity matrix there. Okay? We know that A is filled with constants. I, the identity matrix, filled with constants, right? Okay. B is filled with constants for this LTI system. XK and UK are decision variables. Okay? That means that if my decision variables here are only multiplied by constants, is it linear?
Yes.
It will be. But what did I not mention? Delta t. So if delta t is a constant, then it's a linear constraint. This constraint is linear. And since delta t is equal to capital T, which is your total time horizon, over the number of nodes you have, this is your time horizon, over the number of nodes you have minus 1. These are knot points, number of knot points, sometimes called nodes. Okay. That means if number of nodes is a constant, oh goodness, number of nodes is a constant, and the time horizon is a constant, linear constraint. Do we like linear constraints? I do. It's up to you. But they're useful. So that's why I talk about if our time horizon is a constant, it can make these constraints linear. That's why. So this is why MPC has a constant and receding time horizon. Okay? So that's the math for setting up the constraints. Now, I set it up with Euler's method, forward Euler. What's another method that we talked about other than forward Euler? That is a variable time step solver. That's true, but not what we talked about for direct collocation. Anything we talked about for direct collocation. What are the other methods? I'll give you a hint. One of them is forward Euler. Backward Euler was another one. We talked, did I wax poetic about the future? People remember this? Getting a state from the future? No one remember? Okay. I gotta punch up my metaphors. What's up?
Was it implicit Euler?
Implicit Euler, also called backward Euler. Yeah, either word is fine. Forward Euler is explicit Euler. Backward Euler was implicit Euler. Perfect notes. Okay. You could choose a different method, right? There's another method. Anyone remember another method we used? We talked about? Rhymes with trapezoidal. Trapezoidal. Okay. Basically, those all basically come from different ways of doing integrals, right? People remember forward rectangular, backward rectangular, trapezoidal integration. Comes from the same thing you learned in Calc 2. Okay? But anyway, you could choose a different method of integration, but still gives you linear constraints. Isn't that nice? Okay. So those are for your constraints. We also have to worry about our cost function. I guess I didn't cover the decision variables. Let's put the decision variables W. And as Angela said, or for a direct collocation scheme, what do we need to include in our decision vector?
Input,
Inputs and
states.
U1 through UN, X1 through Xn, right? Hence why these are decision variables. Okay? All right. Again, this is all key to making sure that you have a fast-solving trajectory optimization. Okay? People remember my drone video? Okay, you know what? I'm going to show the drone video. Much more visual. Here we go. Here we go. You see that? So yeah. Here we go. This is my drone video. Look at that. Shoot. Shoot. MPC. What's that?
Are you trying to whack it?
Yeah.
Oh.
Why not? Yeah. Yeah. This is we took a pendulum and we just kept swinging back and forth. Okay. So this is using model-predictive control. It's coming up with a plan to go to a goal. What this particular paper was doing was saying, hey, how do you avoid obstacles along the way? See that big line that's being drawn around there? That was to make a linear constraint to avoid the obstacle. We like linear constraints, right? So it turns out it's pretty good. And look at that. Look at that. Yeah. Look at that. Look at the dodging in and out. It works in 3D. Okay. All right. This is just one of our papers, and there's a whole world of methods people use for model predictive control. Okay. Use it for walking. I can show up that. Videos are fun. Videos are fun. Let me pull up an experiment we did. Okay. All right. The blue drone's using MPC to try to get to the center of the arena. That red drone's using PD to chase it down. So the blue drone's smarter. Okay. And you can see the motion plans we're talking about. That's the motion plan. See how fast it's changing? Every time it changes, it's run a new quadratic program. Redraw it. Yeah. Look at that. Look at that. You stupid red. Yeah. Be kind to it. Be kind to it. We chose those gains ourselves. Thank you very much. All right. It works in 3D pretty well.
It's fun.
Yeah. Pretty cool, right? Show you what it's like. This is maybe a little more dynamic than Hunter. Trying to chase me down.
Ouch.
Yeah. Sorry, Hunter. I did restrict you. I think you would have taken it, to be honest. Yes, Bill?
So you could do this to come up with like a plan, but is there also like a layer of like, how do you get the drone to actually move?
Well, that's a great question. So the question is, that comes up with a plan, but how do you get the drone to move? Okay. Well, keep in mind that in this system we had a U of t in there that's being planned, right? And that U of t is our control input, and that's what we're sending to the drone, right? So there is something you are picking up on something important. It's kind of an underlying layer. Is that the core flight control already exists for that drone. It's a very well-established method called a Mellinger controller that basically just says, hey, if we want to move forward, how do we move forward a little bit? And it comes up with a way to tilt the rotors and make it move, right? So instead of our control input for our trajectory optimization, instead of it being, it is U, but instead of U being, I don't know, motor speed, okay, it actually was desired position next to the drone. And then we send that desired position to a lower level controller, this Mellinger controller, okay, that's able to take that command and turn it into little rotor spinning, okay.
And those are like available, like you didn't have to come up with your
You
own?
didn't have to come up, that's the reason drones are so awesome these days, is because that Mellinger controller is so, it was a game changer. I don't know how many thousands of citations it has, but if you look up Mellinger, M-E-L-L-I-N-G-R, it's called I think it's a method for minimum snap trajectory generation, okay? This is a fun aside, so I'm gonna keep going with it, okay? Minimum snap, interesting. So in mechanical systems, we often talk about F equals ma, right? Pretty famous equation. Force is, so basically you apply a force and you get an acceleration, right? So it's a second order system. So you have to take two integrations to get to the position from acceleration, right? So a lot of times we deal with second order systems, when I'm throwing my pencil around or whatever, okay? So if I'm moving this around, I apply a force, I get an acceleration. I integrate twice, double integration, I get position, right? However, for a drone to move in a direction, it doesn't just go, like this. It has to tilt first to make the rotors go in some direction. And then that creates the acceleration to the right. So in effect, you have not a second order system, even if you're just in a plane like this. You have to add two more orders to basically apply an angular acceleration to the tilt first, and then it moves, okay? So a fourth order system, okay? So that means you're not dealing with positions, velocities, accelerations only. You're also dealing with two more derivatives. Anyone know what the derivative of acceleration is called?
Jerk.
Jerk. We have one more derivative.
Snap.
Snap is what the next derivative is called, right? Next derivative is crackle. Next derivative is pop, okay? I wish I was making that up. I know I told some of you before, or you know this fact. It's a cool one, right? That's why it's called minimum snap trajectory generation. Because on a drone, you care about the fourth derivative position, snap, okay? Right? Anyway, so you can look up the Mellinger controller. It has to do with differential flatness and stuff I don't have time to cover today. But you're right, Logan, that sometimes you need to be clever about what you decide the control input is to your system, right? It can be torques to your motors that you can control, okay? Or if you wanted it to be, it could be a desired position of your motor that's being controlled by a simple PD controllers, for instance, right? We all remember PD controller proportional derivative? Yeah, right? You could just say, here's my proportional derivative controller for each of my motors. So you choose a desired angle for your motor, it goes there, there, there. But who decides what the desired angle is? We do. Or an optimization could. Right? In fact, this is going on a bit of a tangent, but I think it's informative. And I apologize if it's a little bit robot-centric. Every robot video you've ever seen, the coolest robot videos in the world of your humanoids doing flips or there's new ones doing dances. China is really investing a lot in humanoid robots doing all kinds of interesting feats these days. There are a lot of companies involved. But every single one of them, as far as we know, we don't know the secrets internally, but we can infer. I would be willing to wager that every single one of these those control schemes, at the core, has a PD controller on every joint. And there is an algorithm that's just choosing, hey, what angles do I want? Okay. Which is analogous to what I talked about, Logan, with the drone. Our control input is, hey, how far forward do we move, right? And there's some lower level controller, like the Mellinger controller or the PD controller, that's making it do that. Okay. So you'll see people post videos, these things like, oh my goodness, AI has gone so far, and it has. Reinforcement learning has gone really far, particularly with these robots and others. But at the core is some low-level PD controller. And then the higher level fancy algorithm, whether it be MPC sometimes or deep reinforcement learning and all this cool stuff, it's just saying, hey, here's your desired angle for that joint. PD controller does the rest. So don't let anyone tell you that PD and all these classical controllers don't matter. They're using them. They just don't talk about it that much because it's not as interesting. Okay? All right. Tangent over. We have a decision vector. We have our constraints. What are we missing? Cost. cost function. Okay? Now that cost function, who gets to decide it? We do. Okay? So, however, we would like to achieve a convex quadratic programming formulation the cost must be quadratic i.e. has a positive constant Hessian. Okay? Meaning if you take the second derivative of the cost with respect to all your variables, it'll give you a matrix, and that matrix has to what we call a positive definite. Okay? But the way we'll set it up, as long as it's full of constants, you're probably going to be convex. Because here's a good way to do it, all right? Let's do your cost function. And I apologize, I'm going to use f again. Just as a cost function, because we've used it like that before. Okay? Okay? Is going to be equal to the integral. I won't give it the limits just yet. I'll get back to it, okay? Of some x of t transposed q times x of t plus u of t r times u of t dt. Okay. This is a quadratic regulator cost. We introduced this before. But the idea is that this is a cost that effectively takes your states and squares them. Okay? You can kind of think of it as just, you know, first state squared, second state squared. They show up as a big sum of these things. We talked about this a little bit before. Okay? It's just a fancy linear algebra way of writing it, where this Q matrix, like we talked about, has a bunch of constants in it. And the bigger those numbers are, the more it wants to send your states to 0. And the bigger the numbers they are in R, the more it wants to send your inputs to 0. And yes, I've forgotten of t in there. Apologies. It's the sheer excitement of quadratic programming. Okay. So, no, that Q and an R, does that remind you of any controller we briefly talked about in the last 2 weeks? I gave you 2/3 of the answer already.
Riccati?
That's the Riccati equation is how you get this. It's you're on the right track. There was a 3-letter acronym, initialism. It has a Q and an R. And it's for linear systems. A linear quadratic regulator of sorts. LQR, yes, LQR, LQR, right? Talk about LQR, right? That's the cost for LQR. Okay? If your Q is positive, if your R is positive, that'll be a convex cost for your MPC. Okay? Now, you'll notice that I left the integrals blank. In your notes, it went from 0 to infinity, to the very end of time. Okay? We haven't talked how you would derive that formulation. That's okay, it's actually pretty interesting. But we are only looking for the cost over, is it an infinite time horizon? No, it's a fixed time horizon. What letter?
Capital T.
Capital T. Yeah. Right. Say, finite time horizon. Fixed and finite time horizon. Okay. And you can approximate that integral in any number of ways. We've done this before in our coding lecture. Okay? We did it with forward rectangular, right? We've done it with trapezoidal in the supplementary lecture I gave. Okay? So you can approximate it, so you can say that, hey, your cost f of w, which contains all your states and inputs, you could say is equal to the sum from I equals 1 to the number of nodes of quantity xk transpose q xk plus uk transpose r uk times delta t. And that is, technically speaking, I should do it n minus 1 if this is a forward rectangular. Okay? This is an example of a quadratic cost. Who gets to choose Q and R? We do. This is not the only quadratic cost you can come up with. For instance, just look at these numbers. Look at these numbers. Okay. Can anyone with their mathematical intuition tell me what values of xk and uk would give me the lowest cost for this? 0. Yeah. Right? Yeah. If you made them negative, they multiply by themselves and become positive, right? So 0, right? So for this cost function, 0 is the best cost. 0 is the best state to get to. What if you don't want to go to 0? I don't like 0. 0 is a bit clingy. Go away. You could change the cost. You could say that you want your cost instead to be xk minus some x target transpose q times xk minus x target plus uk r uk, all this times delta t, that's transpose, and sum from I equals 1 to n minus 1. Again, the reason I'm doing that is it's approximating the integral of this function via forward rectangular. You got me? So now, which values of xk and uk would have the lowest cost?
And xk is equal to x target.
When xk is equal to x target and uk is equal to 0. So what's this problem going to try to do? Chase down a target while also trying to minimize the amount of effort to do so. Oh, it's almost exactly like what that drone I was showing you was doing, because that's exactly what it was doing. All right, that makes some sense. Any questions? I'll pause for questions here. It's kind of a revelatory once you bring this into play. Think about this. You can just come up with an LTI system. If you have an LTI system, and you have a quadratic cost, you can plan the living daylights out of this out of the system and just keep zipping around, right? And further, who's to say we stop with those constraints that we had? What's important about the constraints for it to be a convex quadratic program? The constraints. What do they need to be?
Linear.
Linear. Do you add more linear constraints? Sure. Why not? So you could add constraints on, say, let's add more linear constraints. What are some ways in which some system might be limited? Has some limitation. Let's say I'm the system. Okay. I'm trying to lift an object. Can I lift it without limits? You shake your head. You have so little faith. I have infinite strength. Wait, I don't. Nothing has infinite strength. So you can have limits. You could say that, hey, UK must be greater than some U minimum and less than some U maximum, right? That's a linear constraint, right? Those are two linear inequality constraints. Totally fine. Is it still a quadratic program? Yeah. This is another reason that MPC is great. It's because it allows you to add constraints. That LQR formulation I showed you before, where U is equal to minus KX, and you come up with the K using the LQR. This is what I did at the very end of the previous lecture, I think. I did that. Maybe something like that. Maybe I did it with LQR with pole placement. You choose a Q, you choose an R. If you know your A and you know your B, you know your K for that controller, right? But LQR knows nothing of limits. It has no idea what its limits are. Okay? Usually we're giving it A, B, Q, and R. Doesn't know any limits. MPC can have limits. So you can add linear constraints. And that's exactly what we did with the drone. Look at this formulation right here. Watch what happens after it. So this is going to dodge around this obstacle. How do we get it to avoid the obstacle? Well, look at that line. I said the state can't go past that line. That's a linear constraint. So look at that. That's the linear constraint changing over time. We just added it in. Can we add it to MPC? Yes, we can. And it's still a quadratic program, still fast.
Is that line saying you can't be within like a certain distance from the, whatever the?
Yeah.
Okay.
Exactly. In fact, you could, one of the tricks for problems like this is like, you might say, hey, why don't we have a constraint that says just don't touch the ball? And that basically would be like a distance constraint, right? You would say, here's where the center of the ball is. The distance to that ball can't be less than this. So x squared plus y squared equals z squared, Pythagorean theorem stuff. What was I just saying? I said square, right? Is that a linear constraint? No. Can't use it. No. So what we did is we said, okay, we don't care that we exactly missed the ball. Let's just miss the line that sort of like is closest to the ball, right? It's actually called a half space approximation. Not part of the course, but it's all part of this game of turning these into linear constraints, right? Okay? We're almost done here. So you can add more linear constraints. These are saturation limits. You can add also, you could add linear constraints to the state as well. You can do that too. But this is the last thing I'll talk about today. You can do that, and it will still be a quadratic program as long as they're linear, right? But be careful. Just because they are linear constraints doesn't mean that they're always a good idea to add. Okay? I'll give you an example, okay? So I'm going to go back to my analogy of trying to get to that target right here. I have a fixed time horizon. Trajectory optimization I'm running, okay? All right? Let's say my time horizon is a minute. And I say, okay, Christian, you have 1 minute to get the trajectory optimization says, how would you get to that target in 1 minute? Okay, great. You must hit that exact target in 1 minute, okay? All right, I can do that. Hey, that's way less than a minute. I can do it, right? The optimization will figure out a way to do it. It's possible, right? But what if my time horizon was 1 millisecond. And the optimization is telling me I have to get to that exact point. I'm sorry, I can't do that. And the optimization will know it. It's like, no, Christian is limited in his puny body from getting there in 1 millisecond. The physics won't line up. It won't get me there. It won't solve that constraint. So you have to be careful on constraints on the state, okay? Because it's completely possible that you asked the system to do something impossible if you're not careful. So that's often why when we have things having to do with state, like getting to that target, we put it in the cost. But if I can't get all the way there, that's all right. The problem will still solve and get me as close as possible, as opposed to saying, you must get exactly there, and therefore it can't solve. And if it can't solve, keep in mind, where is this solving happening? In the middle of this control loop. And you just stop the loop. Is that good? No. This happened this weekend. My student and I had a paper deadline due at 3 a.m. And yeah, they love doing that in robotics. And we're always pushing to get better and better results. And we're about to submit this paper. It's like 1 in the morning. It was on Saturday, technically Sunday at that point. And we were on Zoom, and he was running the experiment in the lab. He was running MPC. And like the data just didn't make sense. And he realized, oh my goodness, the quadratic program wasn't solving, or it was taking too long to solve. And it was because of things like this. So at the last minute, we was like, okay, we got to change the constraint. Boom, and it worked, right? Got it just under the wire, right? So we got to be careful with state constraints, all right? Okay, that's all I got. I've run a few minutes over. Thank you very much for your time. Have a great day.
Is that for AM deadline just because of like different time zones?